find the derivative of soft plus and its domain of definition. So soft plus is, just by looking, initial observation, it's a composite function. So it's a function inside of a function. So ln inside of 1 plus e to the x. Which means we need to know how to differentiate composite functions. Furthermore, we need to know what the derivative for ln of x is and what the derivative for 1 plus e to the x is or will be. So I have these ingredients with me, and we will use it to cook up the solution. There will also be some talk on the domain of definition for this function. We will clarify this once it is obvious to us and what the function looks like. So let us indeed take the derivative of soft plus. For this we'll apply number 1, which is the chain rule. So we need to find the derivative of ln of x. Maybe first I'll write down soft plus. So soft plus is equal to ln of 1 plus e to the x. So I can write this as ln of x, but you just plug in 1 plus e to the x inside. And then, okay, and then I'll return this back in. And then the derivative is going to be the derivative of the outside function, which is ln of x. But you need to compose it with the inside function, which is 1 plus e to the x. And then you multiply this whole thing by the derivative of the inside function. So that is very key for the solution. I'm just applying the chain rule. I have not computed any derivatives so far. I need to compute 2 more. Well, ln of x is 1 over x. So I get, inside the red brackets, I get 1 over x. And I still need to compose it with 1 plus e to the x. Composing means I just need to plug in 1 plus e to the x into 1 over x. And the derivative of 1 plus e to the x is just the derivative of 1 plus the derivative of e to the x. Since 1 is a constant, then its derivative is 0, and we can ignore it. And we just focus on the derivative of e to the x, which is e to the x. And now it remains to plug in. So we get 1 over 1 plus e to the x times e to the x. So I'll just write it here. And I hope you don't mind if I do this, because I see this is 1 plus e to the x, and I see this is e to the x. So I'll just do a very simple manipulation. This is, by the way, it's not part of the solution. You can finish here, this is correct, and find the domain. But what I'm doing right now is I'm trying to make a better case for why the domain is going to be what I want to say it's going to be. This will become clear in a moment. So what I'm going to do here is I'm going to add 1 to match the denominator, and I will take away 1 because I can't really add 1 out of thin air, but I can add 0. So this is equal to 0. And so this cancels out and gives me 1. but I still need to add the minus 1 that I just took divided by 1 plus e to the x. And I hope you don't mind if I just put this minus here. And now, if you want to look at the domain of the definition of this derivative, this one or this one, because they're exactly the same, I can divide by e to the x plus 1 because I know that this value is always greater than 1, because e to the x is always greater than 0. So I don't need to worry about dividing by 0, for example. And for this exact same reason, 1 plus e to the x is always greater than or equal to 1 for any x. So for any x, this means for all x, we've talked about it. And if that is true, then this function is defined everywhere, and there are no possible, let's say, singularities or discontinuities. It's well defined, and it has as much space as it can in terms of the domain. So its domain is just R. Domain of, I don't want to write soft plus prime, but I'll write soft plus prime is all real numbers. That's the second thing we wanted to find from this problem. And the first thing was the actual derivative, which is what you can see here. Or that one, because they're all the same and it doesn't really make a difference.